Hi guys, this is lecture 8 for Chem 223. I wanted to start off with just a quick spiritual story from my life. When I was in high school, I was trying to get myself into reading my scriptures daily and saying my prayers when I woke up and went to sleep. One day, after a particularly long day, strenuous day, I laid down in bed and felt too tired to roll over and say a prayer. And so I laid there contemplating what to do for a moment, and the thought or impression came to my mind that, really, the words came to my mind, I don't care whether or not you roll over. I really just want to hear what you have to say. And that experience impacted me a lot. I rolled over immediately and I said my prayer. And I felt a great amount of love. And I feel like that was an experience where Heavenly Father interacted with me on a personal level. And that is one of the experiences that has helped shape my testimony in Heavenly Father and Jesus Christ, and one of the experiences that has enabled me to hold on to my testimony when life gets hard or when I go through various obstacles or situations. All right, let's get into our lecture now. Today's lecture will be on pH-related topics. So this will include indicators, a little bit about Lab 2, and a little bit about buffers and the Henderson-Hasselbalch equation. I used too many ands in that sentence, but that's life. I used the but in that sentence. All right, this is the molecular structure of bromocresol green, one of the indicators used in Lab 2. You'll notice that this guy has a proton right here, or an OH group. This looks like an alcohol group, and this one is actually similar to it. But because of the conjugation in this molecule, the bromocresol green can actually give up this proton right here. And so this indicator is actually an acid overall. And most pH indicators are acids and bases in and of themselves. And so they are able to change color as the acid either protonates them or the base deprotonates them. And the point at which they change color is determined by the pKa of the indicator, and that determines the pH at your endpoint of your titration. So bromocresol green has a pKa of 4.7, okay? So this form right here is actually bromocresol green's yellow form. Bromocresol green actually doesn't have a green form, it only has a yellow and blue form. So when it is protonated, it is yellow. And when it's deprotonated and that proton flies off, what happens is now you have this lone pair of electrons up here giving this oxygen a negative charge. And this can actually conjugate through the rest of this molecule and change our electronic structure. The reason this is important is because the thing that gives organic molecules their color is generally their conjugation system. So if you change the conjugation of an organic molecule like this, you generally change the color. Now, whether that change is dramatic enough to be seen by the naked eye or not depends on the specific molecule, but we specifically choose molecules to use as indicators that are very bright color-wise and that are easy to see and have a significant change in color. So now that this is deprotonated and its electronic structure is changed, it's now blue. One thing I'll point out that I think is incredible about this molecule is that if it then comes in contact with a proton, or the pH gets low enough that there's enough protons, it actually won't pick up the proton on this negatively charged oxygen right here. The proton will still go back on this oxygen, and that'll cause a series of conjugation changes, and this negative charge right here will actually attach itself right back there, which I think is pretty cool, pretty interesting. All right, anyways, let's talk about this guy functionally. So if we go to pH below the pKa of this molecule, that means that the molecule is going to be protonated. If you're at a pH lower than the pKa of an acid, then the acid is protonated. And so the blue molecule will still exist in there to some extent, the deprotonated form, but the ratio of the yellow to blue molecules will be 10 to 1, meaning there'll be 10 times more protonated molecule than deprotonated. And what that means is that this guy will mostly exist in its yellow form, and what we'll see with our eye is the yellow color. Now, if we go a pH unit above the pKa value, so now we're at a pH value of 5.7, that ratio is flipped. Now there's 10 times more blue molecules than there are yellow, and now we see this as blue, or we see the solution as blue. So just to help you wrap your mind around this, if we went another pH unit below the pKa value, so if we drop to 2.7, then the ratio between yellow and blue would be 100 to 1. And if we went 3 units below, it'd be 1,000 to 1. Anyways, if we're right at the pKa value, so if our pH equals our pKa value, then the ratio of yellow to blue is actually going to be 1 to 1. And so with our eye, we're going to see some yellow color and we're going to see some blue color. And if you remember back from kindergarten, if you mix the yellow paint with the blue paint, you see green, and that's what we see with our eye, and that's what determines the endpoint for bromocresol green. So this actually leads us into what you're going to be doing in Lab 2. In Lab 2, what we have are 4 different indicators: bromothymol blue, bromocresol green, methyl orange, and methyl red. These guys all have different pKa values. So you can see bromothymol blue has a pKa value of 7.1, methyl orange has a pKa value of 3.5, which means these guys are all going to change color at different pHs. So let me show you real fast what their colors look like. So these colors are just generic PowerPoint colors, but it gives you the idea. Both bromothymol blue and bromocresol green start as blue and end up as yellow. And methyl orange and methyl red both start as yellow and end as red. They're not exactly the same colors of red and yellow or blue and yellow, etc., but they're pretty close. But as these guys go down, you actually measure their endpoint at different places. So bromothymol blue, you actually measure its endpoint when it's turned completely yellow. For bromocresol green, you measure its endpoint when it turns green. For methyl orange, when it turns orange, and for methyl red, when it turns red. Now what you can see here, though, these guys, their endpoints are all at different pH values, right? And we're starting these indicators off in a tris solution or in a beaker with tris in it. And tris has a pKa value of 8.08. So it's actually a basic compound. So we're starting with a basic compound. And what we're trying to do is determine the pH of our HCl solution, which has a concentration of 0.1 molar, giving it a pH of 1. So as we start our titration, we start out at a pH of around 8, and we titrate down until we get to a pH of around 1. But really, we're not trying to get all the way down to 1. We actually are going until we hit this endpoint, and then we stop. And so the point of Lab 2 isn't actually to determine the concentration of the HCl solution. That is something you're going to have to do through your titration. But really, the question is does it matter which indicator I use? Is that going to affect the concentration I get out for my hydrochloric acid? And the real reason we do this lab actually is so that we can collect a big sample of real data that you can use to analyze using statistics, and you're going to tell us statistically if you get these same results with each of these values. So the average HCl concentration you're going to get for each one is going to be different, but you're also going to have a standard deviation associated with that average, and then you're going to have to do an F-test and a T-test to figure out if statistically they are from the same population or different populations. One other thing I'll throw in here is that these indicators all change color between the 2 terminal pHs, right? If you use something like phenolphthalein that starts being a vibrant purple and goes to colorless, This guy, its color change is very visible, but it's not going to work for us because its pKa value is 9.7, which is above our starting pKa value and is useless. So if you're going to use an indicator for titration, it has to be in between your terminal pH values. And by that, I mean your starting and ending pH values. All right, that does it for lab 2. Now let's talk about buffers. So along with this lecture, just like the previous, there is a handout. So let me go ahead and pull that handout up for you. So this is just a buffers review. It has several questions and answers like the other handouts that you'll want to go through and work through. And of course, whether or not you did this handout will be reported in your online quiz. So make sure to do it. So I'm just going to review a couple things about buffers in this lecture, and then you're going to get the rest of the information from your reading, and you're going to remember a bit of it from that buffers review. I'm sure you knew most of this, but since most of you took chemistry several years ago, you probably forgot a bit of it, and that's why we're going through this review. All right, a buffer is a solution that resists pH changes. So an excellent example of a buffer in real life is your blood, which changes pH very slightly. Even if you add tons of acid or base to your blood, it balances itself out very quickly. So if you ever see a health blog saying you're going to acidify your blood or make your blood more basic or change the pH of your blood, it's just complete nonsense, complete and utter nonsense. Okay, the next thing to remember about buffers is they're generally prepared from an acid conjugate base or base conjugate acid pair, such as acetic acid and sodium acetate. And the pH of a solution equals the pKa of the acid when the acid concentration is equal to the concentration of the conjugate base. This is actually the definition of pKa. pKa is the pH that you get when you have equal concentrations of the acid and base. Buffers are generally considered good, don't lose their pH, or they don't change pH very rapidly when the concentration of acid to conjugate base is within a factor of 10 of each other. This is a good buffer when this ratio is between 0.1 and 10. And then what we call the buffer capacity is the amount of acid or base that you have to add to your buffer to exceed that 10-to-1 ratio of acid to base and to get outside of that range. So once you added more acid or base than that, the pH can change rapidly. So your buffer capacity just describes how well your buffer can hold on to its pH value. The last thing we're going to talk about today is the Henderson-Hasselbalch equation. We're going to go over the derivation for that right now. So the Henderson-Hasselbalch equation, though, is useful for calculating the pH of a buffer solution that you prepare by adding acid and conjugate base or base and conjugate acid. But the way this is derived is we actually start with the equation for Ka. So if you remember, the Ka is the acid dissociation constant, and that's equal to the concentration of protons times the concentration of conjugate base divided by acid concentration. Now, if we take the log of this whole thing, then on the left, we'll now have the log of the Ka value, and on the right, we'll have the log of this ratio, where we have H plus times A minus over HA. Now, if you know your log rules very well, you'll know that we can actually break up this guy on the right and to something that looks like this. So there's a logarithmic identity that says if you have two things multiplied together inside your parentheses, you can pull those apart and then just add them together. So this would be log H plus plus log A minus over HA. And if we wanted to pull this HA out, then we'd do minus the log of HA since we're dividing by. But anyways, this is where we're at now. Now we're going to multiply this whole thing by -1 to get a very surprising result. And the result is, we put negative signs in front of everything. Were you surprised by that result when I said we were going to multiply it by -1? All right, now that we have all of these with a negative sign in front of them, though, You might recognize some parts of this. The negative log of your Ka and your negative log of your H plus concentration. These are actually equal to your pKa value and your pH values. And so now we have pK equals pH minus the negative log of your conjugate acid or conjugate base concentration divided by your acid concentration. If we simply add this side or this logarithm to the other side, we have the final form of the Henderson-Hasselbalch equation. So this is your pH being equal to pKa plus the log of your conjugate base divided by your conjugate acid. And so we'd use this to determine the pH of, let's say we're looking for an acetic acid acetate buffer solution. So we added 0.1 molar sodium acetate and 0.5 molar acetic acid. We'd plug the 0.1 into the top part here, the 0.5 into the bottom. We'd look up the pKa value for acetic acid and plug that in, and this equation would then give us the pH of our solution.